our recent efforts about the application of those different types of entangled photon sources. The first one is an entanglement enhanced microscope. The second one is toward ultra high resolution quantum OCT. And if I still have time, I would like to also add some recent information, and then I would like to conclude my talk. So, as all of us know, quantum entanglement is the superposition of different states of the correlated particles or photons, and the quantum state of each particular photon cannot be described independently. And actually, entanglement can be found in not only in polarization, but also in many different degrees of freedom, like frequency or color, photon number in path, and angular momentum. And the application of those entangled states are also in various fields, like quantum communication, quantum computation, and quantum metrology. And one note I would like to give is that photonic quantum circuit or multi-photon path interference is very useful to generate many different types of entangled states. This is an example. We developed an entanglement filter some years ago using this sort of optical quantum circuit, combining some quantum phase space. And then I would like to enter into the first main topic, entanglement enhanced microscope. So, as we know, optical phase measurement is very useful in many fields, like gravity wave detection or gyroscope for aircraft, and also even in cosmology, this microscope is actually using optical interferometer sitting here to enhance the sensitivity. And there are two important concepts. One is sensitivity and one is precision. And it is very important that there is basically no limitation for better precision. In order to improve the precision, what you have to do is you have to use more resources. Using larger number of photons, one can get better precision at will, in principle. However, there exists a limitation for sensitivity. Here, sensitivity is precision divided by number of resources. Okay, so then the question is, with a given number of photons, how much is the minimum uncertainty for the phase information? This issue was actually discussed in this Nature paper and later in this Andrew White's paper in PRA 2007. And when you use classical light or stream of single photons, the phase uncertainty you can get is given like this: delta phi equals to 1 over square root n. This is so-called standard quantum limit or short noise limit. However, when you use entangled state of photons, this is one example, noon state. In this case, the delta phi is now 1 over n. This is so-called Heisenberg limit. So you can enjoy the improvement from 1 over square root n to 1 over n. And some people may think this difference is not exponential, therefore may not be useful so much, but it's not true. So in an ultimate limit, in very far future maybe, now we have a kind of measurement using 1 joule of photons could be reduced to 1 nanojoule of photons if we could have an extremely larger number of entangled states. Even when we have just entangled states with 10 photons, as I will show you later, the sensitivity can be enhanced by a factor of 3 or even more. So this sort of advantage could be maybe useful when faint light probe is necessary. So we are interested in the application of this sort of technology in biology. And some years ago, we demonstrated four-photon interference experiments using this discretionary interferometer, and we generated using post-selection this sort of superposition state for +0,4 state, and here this four-photon state is rotating like this, and rotating like this, and this is a superposition of these two possibilities. And the observed interference fringe recorded high visibility of 91%. This is better than the threshold visibility of 82% to beat the standard containment. And this result was somehow interesting in some people like this. However, I have some comments from people, especially in different fields, that this demonstration could be interesting. However, it is very difficult for them to imagine how we are able to use this sort of technology in real life. So, and this entanglement enhanced microscope is our answer to such kind of questions, and we proposed and demonstrated. This work was done with Dr. Takafumi Ono, and now he's in Bristol, and Professor Ryo Okamoto. He's now in Kyoto University with us. Differential interference contrast microscope is a very useful tool because it can be used to enhance the contrast in unstained transparent samples. Therefore, the differential interference contrast microscope is widely used to observe living cells or living tissues or unstained biological samples. And it is also important to note that DIC can not only be used to observe something, but it can be used to sense the small change in density, volume, or chemical contents in the medium. And this is one example of the application of DIM, especially laser confocal microscope type differential interference microscope. This was done in Hokkaido University. A unit step on ice crystal surface has been directly observed using this technology. It's very difficult to observe the monolayer development of ice in water, actually. And signal to noise ratio of this sort of technology actually determines the depth resolution limit of this microscope. And this is how LCM DIM works. So the light for illumination is divided into two optical passes according to its polarization, H and V, using this polarizing prism, and then focused into two different spots, adjacent two different spots, and then recombined again by another polarizing beam splitter here. Therefore, this is a kind of interferometer, right? And when you scan these two spots on the sample with this kind of structure, then what happens is that at the edge of or step of this sample, you will see the path length difference between this spot and this spot. Therefore, you have the change in detection events here. And the opposite happens in this side. So you can have this sort of signals by making a kind of image using this data. You can observe the kind of image this this is working principle. And then let's consider the case where probe light intensity is kind of limited. So this is a calculation with 14,000 photons for each point or for each spot. In this case, this is the theoretical curve. However, due to the short noise or fluctuation, statistical fluctuation of photon numbers, you observe this sort of noise, right? And when the number of photons for each point is reduced to, for example, 140, then now you are not able to see the signal in this noise, right? So this is the limit. And in order to improve this situation, we propose to use entangled state for illumination, and also replace the detector of light to the coincidence detection using photon detectors. In this case, signal is given by the change in phase times this slope, but slope is now twice larger than the normal sinusoidal curve, right? And the noise is given by delta C. So signal to noise ratio is calculated like this, but this term delta C over delta phi divided by delta C is depending on the source and detection schemes you are using. In case of quantum or entangled state, SNR is n times delta phi, but classical case SNR is square root n times delta phi. So by using entangled photons, SNR can be improved by a factor of square root of n. Here, n is the number of photons in one entangled state. And this is how we are able to achieve the improvement with entangled photon or null state. This is a classical light case, and this is the case where we have two-photon entangled state. Please note that the background level is half of this classical light case. However, the height of signal is maintained in this case. Therefore, as you observe, the fluctuation in background is larger in classical case. Therefore, SNR is worse than this entanglement microscope case. And in future, if we could have 10-photon null state or related quantum state of photons, contrast will be greatly improved, as shown here. And this is our experimental setup. We generated percent-entangled state using this pair of BBO crystal and calcite crystals here, and then injected onto the sample, and then recombined using this calcite. And the quality of percent-entangled state is fidelity of 98%. And we also this is the observation at the spot. This is classical light field, but these two beams are focused on at the sample with 45 micron diameter of beam, adjacent with 45 micron again. And this is the actual setup we used. This is the entangled photon generator, and this is the ICM setup. But please note, this can be in principle easily replaced with actual optical microscope. And these are interference fringes we observed for single photon interference and two-photon interference using the setup. And visibility of single photon interference was 97%, and visibility for two-photon interference with this experiment is 95%. Even when we have lots of optics to make such kind of adjacent focus. And with these actual interference bridge data, we set our bias phase point to the optimal to gain the maximum sensitivity. The details of the theory is given in this New Journal Physics paper in 2008. And we selected the optimal bias phase point for this single photon case and two-photon interference case. And this is the sample we used, a glass plate sample on whose surface a Q-shape is carved in relief with an ultra-thin step of 17 nanometer using optical lithography. This is about 100 atoms, right? And we scanned these two laser spots like this. And this is the image we got using our setup. And note that average total photon number was set to 920 photon per pixel, and one pixel size is 20 micron times 20 micron. And this is classical case. You can observe the Q shape, but very noisy, right? And if you are kind, maybe you could observe some difference between these two graphs. So this is the case where we used the same number of photons, but entangled photons and coincident detection. Q is slightly more visible here. The quantum image has a better contrast. And then in the next slide, we tried to have a quantitative evaluation of the contrast. These two graphs are the actual data we observed in these two sections, right? And from this data, we are able to calculate the signal-to-noise ratio directly using these statistical fluctuations and this signal height. And the result is that SNR we calculated with this data is 1.58, and SNR for quantum is 2.13. So the ratio of improvement factor is calculated by 1.35 plus minus 0.12. And this is ultimately can be 1.44 square root 2 when we use two-photon noon state. However, as I have shown you, our visibility is high but limited to 95%. And also, we still have some overlap of the adjustment beams. If we include those factors, theoretical prediction is 1.35. So this result matches to the theoretical prediction pretty nicely. And also, we are using these data, we are able to estimate the height of this gap using these two results. And estimated height with this data is 16.6, and this data is 17.0. And the AFM estimation is 17.3. The important point is that the error is reduced when you use quantum microscope. So enhanced microscope can estimate the step height with better precision for the given probe intensity. So this is a bit interesting that they say the microscope exploits spooky action at a distance. So interestingly, in Japan, people said entanglement is too difficult to understand. So they are not able to show us some interest, but maybe in physics world or some journals in Europe, they reported our results. Then I'd like to move to the second topic, our effort to realize ultra-high resolution quantum optical coherence tomography. This is about entangled photons, but now entangled in frequency region. And monocycle entangled photons is a state where two photons are created in a very short time, a few femtoseconds, only one cycle of light oscillation. And once this kind of state is realized, application may include quantum optical coherence tomography or giant two-photon absorption, or may be useful for clock synchronization. Theory is given in this paper. And then I would like to explain the difference of monocycle entangled photons with other bit similar states. This is single photons state, this is weak coherent light field. In this case, single photons appears at random in time. And this is a case where attenuated monocycle pulse laser. In this case, you have these optical pulses with very high precision, with a few femtoseconds, but the number of photons in each pulse is not determined, or you have Poissonian distribution. And our monocycle entangled photon state is like this. So these two photons are always found at the same time within a few femtoseconds, but the two photons are at random in time. And another important feature is that you can see the change of colors, difference in colors between this guy and this guy. And this guy is each photon has different same kind of frequency distribution, but in this case you have a correlation in frequency between these two photons. Okay. And in order to realize this sort of state, this is monocycle entangled photons in time space and in frequency space. In order to have very high correlation in time, you need ultra broadband width. This is a Fourier transform relation. So bandwidth should be very broad. In order to realize such a ultra broad parametric fluorescence, we collaborated with Professor Kurimura's group at NIMS Japan, and they fabricated special stoichiometric lithium tantalate QPM device with extremely large sharp of 10%. And we tested this sample with pump beam of 532 nanometer. And this is the result. This is the observed spectrum of the parametric fluorescence using a superconducting detector. This is with the help of Nanjing University with Professor P.H. Wu and Professor Jian Chen. And this is with the help of Hammer's photonics. It is because in order to observe such a ultra broadband bandwidth, we need special detectors like SNSPD or ultra broadband photomultipliers. And from each of data, we confirmed that the emission is from 790 to 1610. This is more than 1 octave. Right? So we observed ultra broadband parametric fluorescence in non-collinear condition. This corresponds to the 1.1 cycle of light oscillation if we are able to control all the phase information of these states. Then now we are also trying to use this sort of ultra broadband entangled photons for quantum optical coherence tomography. Currently, optical coherence tomography using low coherence interference is widely used in many fields, especially to observe the condition of retina in your eye. However, and very important tool now, But there is a resolution limit about 10 micron. The reason I will show you later. And more than 10 years ago, people in Boston University proposed to use two-photon interference of frequency correlated photons instead of low coherence interference. And they proposed quantum OCT. And they suggested that two-photon interference leads to less than 1 micron, even under dispersion. And then I would like to explain why resolution is limited in case of OCT. In order to improve the resolution, what you have to do is you have to extend the bandwidth of optical field you used for OCT. But if you increase the bandwidth, at first you are able to minimize the resolution. However, at some point, you will observe huge effect of dispersion in the media when you increase the bandwidth. And actual resolution is degraded very rapidly when you increase the resolution. So there is a kind of optimum point like 10 or 20 micron. But QOCT has two interesting features. The first one is for a given bandwidth, QOCT resolution is better than optical coherence tomography resolution. The second point is even order dispersion are cancelled when you are looking at the home and lip with frequency entangled photons. However, Boston group has been working on this issue many years, but there are still unclarified issues or unrealized issues. The first issue is that increment factor is reported by Boston group and Professor Lesch's group in Waterloo, but the reported ones are different, square root 2 or 2. And the second one is dispersion cancellation has been demonstrated by Boston group, but their resolution is still 20 micron and in a sense low resolution region. So we looked at these two issues. And in order to test experimentally, we also constructed optical coherence tomography and quantum optical coherence tomography hybrid experimental setup. By using this setup, we are able to perform both OCT and QOCT experiments using the same light source. And the details can be found in this paper in 2013. And in this experiment, we used broadband, a little bit broadband frequency entangled photon pairs generated with this Libio type 1 crystal. And this is the result. We found that actually I don't have the slides about this issue, but we found that this increment factor depends on the shape of your spectrum of entangled photons. If it's rectangular, the enhancement factor is 2, and if it's Gaussian, it should be square root 2. And we also demonstrated the change of factors using different types of spectral bandwidth. And we also found that line width of pump laser for parametric fluorescence is very important if you are going into the very high resolution region. Therefore, in this experiment, we used very small line width of 100 kHz for pumping as pumping laser, and these are results. In case of OCT, the resolution was 4.2 micron at first, but when we insert 25 millimeter thick water, this is about the size of eyeball, this resolution is degraded to 37 micron. However, if we use very small lines of laser pumping, we observed 3 micron resolution in quantum OCT signal, and even when we inserted water, resolution is not changed at all in this region. And we also performed, okay, so dispersion cancellation is demonstrated in high resolution region now with 3 micron, okay. And we also succeeded in getting some images using this 3 micron resolution OCT setup. And in case of OCT, this sample image is strongly degraded. Resolution becomes, in this case, 4.6 micron, but in this case, the resolution is 63. Right? So strongly degraded when we put zinc selen plate in the optical setup, which corresponds to 40 nanometer thick water. And in case of QCT, as I have shown you, we don't see almost any degradation in images. And we are now going further. With the help of Professor Klimra and his collaborators in NIMS, we were able to develop a special QPM device for visible wavelengths. And we demonstrated the generation of ultra broadband. Now it's in almost visible wavelengths. And the center wavelength is 800 nanometer. This is widely used for real optical coherence tomography setup for eye observation. And then we performed the similar experiment using this ultra broadband parametric fluorescence in visible wavelengths. And these are brand new results. In case of QCT, this is experimental data. We observed 0.54 micron resolution. And this is just simulation of OCT. In this case, maybe the resolution is 1.1 micron. The enhancement factor is almost 2 because the shape of the spectrum is almost rectangular. And this is the case when we inserted 1 millimeter thick water. We observed very slight degradation from 0.54 to 0.56. However, in case of OCT, the signal will be degraded into 3.3 micron. So now we are able to observe ultra narrow home and lip of the resolution of 0.54 micron for QOCT, surpassing the record of classical OCT resolution of 0.75 micron. But please also note that this OCT signal is without any dispersion tolerance. So they are not able to use this sort of signal for actual observation, for example, IDH. Okay, so I still have a few minutes, so I just want to also show some other recent topics. The first one is we are able to demonstrate implementation of a quantum-controlled swap gate with photonic quantum circuit. And actually, this is a kind of, we used different strategy from the group of Jeff in Griffith University. They are going to show their most updated data tomorrow. But two groups are using different strategies. Our strategy was proposed by Fluorescence some years ago. Actually, Fluorescence's group demonstrated partial swap gate using this Manhattan interferometer setup, and he proposed to replace this pi. In his experiment, he put pi by putting some optical phase plates. but he proposed theoretically that if we could replace this one with controlled phase gates, we are able to perform controlled swap gate operation, and we succeeded in implementing this bit complicated optical photonic quantum circuit using this displaced architecture and specially designed a set of polarizing beam splitters. Here, half of the beam splitter is one TPBS, and another half is mirror or just simple beam splitters. And we recorded competence-based fidelity of 0.85, and we also checked the generated GHZ state has fidelity of 0.81. And using those results, we estimated process fidelity of this C-swap operation of 0.77. This will be submitted soon. Another topic is nano-fiber Bragg cavity and coupling quantum dot onto this nano-fiber Bragg cavity. We fabricated our Bragg cavity in a tapered optical fiber with 300 nanometer diameter. And this is the actual scanning ion image of the device we fabricated. And one interesting feature of this device is that we are able to tune the resonant frequency over very broad, wide frequency region, over 20 nanometer. And this frequency change can be done repeatedly. And there are not so many solid-state microcavities which has this sort of tuning capability. And we put a quantum dot on this structured non-fiber Bragg cavity and observed the emission of single photon by factor of 2.7 when compared to without partial enhancement. And actually, without this structure, we observed the coupling of 7% from quantum dot to the tapered fiber. And later, Professor Hakuta in Tokyo reported that actually 7% is underestimation. If we take account the real quantum efficiency of quantum dot, the coupling efficiency to the single mode of the fiber was 20%. So if you take into account this 2.7 factor, and if we have a narrow line single photon emitter, the coupling factor could be more than 50%. And with this into single mode of the fiber. And our Q factor of this device is limited to 130 due to the due to some technological issues. But we hope that we are able to improve the Q factor soon, and hope that we could have single photon sources more than 90% coupling efficiency into the single mode of the fiber. Okay, so this is the summary of my talk. In the first part, we reported entanglement enhanced microscope, and in the second part was the high resolution quantum oscillator. And I would like to also thank these collaborators work together with us, and also funding agencies. And thank you very much for your attention.
Thank you very much. Some fantastic results there. Do we have any questions for our speakers? No, I just had it first.
Yeah. Thanks very much. That's very interesting. Question about the fiber cavity.
Okay.
Did you mention how it's actually fabricated?
Okay. Yeah. Actually, this paper appeared this week. So maybe please take a look at the details about in this paper. But we fabricated this one, putting this 300 nanometer fiber into the FIB, FIB and curved on the surface, upper surface using FIB.
Yeah. Thanks.
focused ion beam.
Ah, thank you.
Do we have any more questions?
Andrew, didn't you have your question?
That was close.
Okay.
Okay, in the interest of time, no more questions. Andrew?
Okay, then a follow-up. What do you think is limiting the coupling at the moment?
You mean this wavelength tuning?
Yeah.
It's a good question. We are also interested in path limits, but actually the length we stretched is now 300 nanometers. And we are not sure, but we have tried on 25 nanometer in frequency. Center frequency of 6050 is a kind of, what we were able to do with this sort of device. But maybe there might be some way to increase. But for most of the experiments, maybe this tuning range is already okay, I guess.
And what quantum dot did you use?
Now we are using cadmium selenide quantum dot, but we are thinking to use different type of single photon source.
Okay, let's thank our speaker again.